Hello everyone. In the last class we have studied the DC analysis of MOSFET circuit. In today's class we will do some numericals on MOSFET circuits at DC. Let's start. In the first numerical is given analyze the circuit shown in figure, determine the voltage at all nodes, drain current and transconductance of the MOSFET. Let's threshold voltage is given 1 volt and mu Cox W by L is given 1 milliampere per volt square, and neglect the channel length modulation effect. 10 volt DC supply is given to bias this circuit, and RD is given 6 kilo ohm, RS is given 6 kilo ohm, R1 R2 is given 10 mega ohm. Now in these circuits the drain current ID will pass through RD and RS. Same drain current ID will pass through IDR and RS. The gate terminal is separated by dielectric material from source and drain. So gate current is 0. So we can write Ig equals to 0. These R1, R2 are dividing the supply potential 10 volt. So at gate terminal we can find out the Vg equals to VDD into R2 by R1 plus R2. That means Vg will become 5 volt. Now let's assume that in this circuit the transistor is working in saturation region and gate potential and is 5 volt. We have find out that. So VGS is Vg minus Vs. Vs is the potential drop across this resistor Rs. So Vs equals to Id into Rs. So you can write VGS equals to Vg minus Id into Rs equals to 5 minus 6 Id. And as this transistor is working in saturation region, so ID equals to, we can say, mu Cox by 2 into W by L into VGS minus VT whole square, and channel length modulation effect is neglected. In the numerical, it has given mu Cox W by L equals to 1 milliampere per volt square and threshold voltage is given 1 volt. So we can find out ID. ID equals to, we can say 0.5 into 1 into 5 minus 6 ID minus 1 whole square. After that we will get a equation that will give 18 ID square minus 25 ID plus 8 equals to 0. From this equation we will get drain current value, two values. One drain current will give ID equals to 0.89 milliampere and another drain current will be ID equals to 0.5 milliampere. So if I consider the drain current is 0.89 milliampere, then we can see that Vs source potential Vs equals to 6 into 0.89 equals to 5.34 volt. So Vs is greater than Vg. So this transistor is not switched on as Vs is greater than Vg. But this is a NMOS transistor. So to switch on this transistor, that Vg should be positive. That means VGS should be positive. So this ID is not right. So we will consider that ID equals to, the ID value is 0.5 milliampere. So Vs will become 3 volt and VGS we can find out that it will become 2 volt. Drain potential Vd equals to 10 minus, that is VDD minus the potential drop across RD, that will become 7 volt. So VDS equals to Vd minus Vs, that will give you 4 volt. Now we know that to work the transistor in saturation region, VDS should be greater than VGS minus VT. and here VDS is 4 volt and VGS is 2 volt and threshold voltage Vt is 1 volt. So VGS minus Vt is 1 volt. That means the VDS is greater than VGS minus Vt. That means the transistor is actually working in saturation region. So our initial assumption is right. Now, after finding out VGS, we can use the transconductance equations Gm equals to mu Cox W by L into VGS minus VT here, and we can find out the transconductance of the MOSFET, that is 1 milliampere per volt. Now let's do another numericals. In this numerical design, it has been given that design the circuit given below, that is determine the value of RD and RS so that the transistor operates at ID equals to 0.4 milliampere and VD equals to 0.5 volt. The MOSFET NMOS transistor has threshold voltage VT equals to 0.7 volt, mu Cox equals to 100 microampere per volt square, L equals to 1 micrometer and W equals to 32 micrometer. Neglect the channel length modulation effect. So, in this circuit, the gate is connected to uh, ground. So, that means Vg is 0. Vg is 0. Now, this VDD is 2.5 volt and this RS is connected to another supply, that is minus 2.5 volt. So at the drain terminal, it has been given that drain terminal the potential Vd equals to 0.5 volt. As Vd is greater than Vg, so the transistor will work in saturation region because it will satisfy the condition that VDS is greater than VGS minus VT. So we can use the saturation current equation ID equals to mu Cox by 2 into W by L into VGS minus VT whole square. In the numerical, it has been given ID value is 0.4 milliampere, that means 400 microampere. Threshold voltage is 0.7 volt and mu Cox is 100 microampere per volt square, L is 1 microampere and W is 32 microampere. So using these values we can easily find out from this equation that we can find out the VGS, and that will be VGS equals to 1.2 volt. And after finding out VGS, we can find out Vs because VGS is Vg minus Vs. Vg is 0. So Vg is 0. So Vs will become minus 1.2 volt. After finding out Vs, we can find out the Rs value. Let's find out the RD value. To find out RD equals to VDD minus VT by the current passing through this RD, that is ID. So we can find out the RD is 5 kilo ohm. We have already find out the Vs and Vs's value is given. So Rs equals to Vs minus Vss by ID. Vs is minus 1.2 volt. So Rs will become 3.25 value. So in this numerical we have find out the drain resistance value, also the source resistance value by this. In the next class we will do the AC analysis of a common source amplifier circuit. Thank you.